Exercise. Find the distance between the point P, whose coordinates are 3, -1, and 0, and the plane W, whose equation is given by 3x minus 5y plus z equals 0. Solution. We're looking for the distance between the point P and W. Let us call the distance lowercase d. Now, the distance between P and W is the shortest distance between P and any point in the plane, any vector, if you like, in the plane. Now, it is easy to see that such a distance is equal to the distance between P and the projection of P onto W, which I'm denoting here by PROJ PW. Now, that's such a distance, therefore, will be given by what? By the length of the vector P minus the projection of P onto W. Notice that the length is basically denoted by putting two sort of absolute values, right, from to the left and to the right of the vector P minus projection of P onto W. So our main goal, therefore, is, in finding such a distance, is to find the projection of P into W, because we don't know yet what it is. Excellent. So how do we proceed? Well, we know how to find the projection of P into W by the orthogonal decomposition theorem. What does this say? Well, if U1 and U2 is an orthogonal basis for W, then the projection of P onto W is equal to the linear combination of the vectors that form such a basis using as weights C1 and C2, where C1 and C2 can be easily computed. C1 is given by P dot U1 divided by the dot product between U1 and U1, and C2 is equal to P dot U2 divided by U2 dot U2. Excellent. So now let us think for a second. In fact, you're welcome to stop here the video and to think on your own. Do we have a basis for this plane? Yes or no? The answer is not yet. We do not have yet a basis. In fact, we do not have an orthogonal basis. Well, we are going to find one. And to do so, we're going to do this in 2 steps. So step number 1, we're going to find any basis that works for W. Step number 2, we're going to use step 1. We're going to use the basis that we found, and we're going to build, using the basis from step 1, we're going to build an orthogonal basis for W. All right, let's get started. So from the equation 3x minus 5y plus 3z equals 0, we solve for x. And therefore, we can see simply that x equals 5/3 y minus z. Therefore, we can define u to be equal to any generic vector on the plane, and the vector will have coordinates x given by 5/3 y minus z, y and z, where y and z can just be any real numbers. Okay, so let us continue. So next, what do? We write the generic vector u as follows. We write u as the sum of 2 vectors. One vector is multiplied by y over 3, and that would be the vector 5, 3, 0, plus the vector z multiplied by -1, 0, and 1. Therefore, it follows that the plane W is equal to the span of the 2 vectors. Let's call them v1 and v2, where I'm calling v1 to be equal to the vector -1, 0, 1, and v2 to be equal to the vector 5, 3, 0. You're going to see I chose this order just because it's simpler to do what I'm about to do next. So I check next that if I take the dot product between v1 and v2, I end up with -5, which is not equal to 0. Therefore, v1 is not orthogonal to v2. Therefore, this basis v1, v2 is not good for using the orthogonal decomposition theorem. So I need to move to step 2. You may want to notice that the step 2 is not necessary if the vectors are already orthogonal. But in this case, since they're not orthogonal, we need to do so. So what is step 2 about? Step 2 consists in the following. It consists in creating an orthogonal basis. So what we're going to do is I'm going to say set u1 to be exactly equal to v1, where v1 is the vector negative 1, 0, 1. And now we're going to define a vector that does not exist yet. We're going to define u2 to be equal to the vector v2 minus v2 dot v1 divided by v1 dot v1 multiplied by the vector v1. So what u2 is defining here is define the difference between v2 and this other vector here that I'm pointing out. That would be the projection of the vector v2 onto v1. Now we know that by definition v2 can be decomposed as the sum of two perpendicular vectors, or perhaps by definition of the projection, right? We know that is true. And this tells us that the vector u2 defined as v2 minus the projection are going to be orthogonal to each other. Now, if I do such a calculation, I end up with, let me write down, if I replace all these numbers here, so v2 is 530 minus 530 dot product with the vector negative 1, 0, 1, divide by the dot product between v1 with itself, that's equal to 2, multiplied by the vector negative 1, 0, 1. If I replace all these numbers here, I end up with the vector 5 over 2, 3, and 5 over 2. Now, you can check that if you take the dot product between u2 and u1, you certainly end up with 0, right? Because you have negative 5 over 2 plus 5 over 2. Therefore, thus, the basis beta made by the vectors u1 and u2, let's write them down, negative 1, 0, and 1, and 5 halves, 3, and 5 halves. This is now an orthogonal basis. The handwriting is terrible here, but perhaps you can understand what I mean. That's an orthogonal basis for W. Excellent. Now we're going to use this orthogonal basis, and we're going to use the orthogonal decomposition theorem to find out what the projection of P onto W is. So this is going to be equal to C1 U1 plus C2 U2, where C1 will be given by what? C1 will be given by the point, so which is, in my case, the point is 3, negative 1, and 0, dot product with the vector negative 1, 0, 1, divide by the vector negative 1, 0, 1 multiplied by self, negative 1, 0, 1, so it will be the norm squared. So when we do the calculations, we end up with the following result, which is, we can see we get negative 3 in the numerator, and the denominator is just 2, so it's negative 3 halves. And so next we calculate the C2, and so C2 would be equal to the dot product between the point P, so 3, negative 1, 0, with the other vector, which is 5 halves, 3, and 5 halves, divided by the dot product between the vector 5 halves, 3, 5 halves with itself. That turns out to be 43 divided by 2. And then we obtain, when we simplify these numbers, we get 9 over 43. Then we are ready to calculate the projection of P onto W. So that's going to be equal to negative 3 halves, because C1 is negative 3 halves multiplied by the vector negative 1, 0, 1, plus 9 over 43 multiplied by the vector 5 halves, 3, and 5 halves. And therefore we end up with 1 over 43 multiplied by the vector 87, and then 27, and negative 42. Excellent. So we are ready to write down the vector P minus the projection of P onto W. So that will be equal to the vector 3, negative 1, 0, minus the vector 1 over 43, 87, 27, and negative 42. And that will give us 1 over 43 multiplied by the vector 42, negative 70, and 42. Finally, the distance d that we're seeking for is given by the length of the vector p minus the projection of p onto w, which is equal to, by definition, 1 over 43, the square root of 42 squared plus negative 70 squared plus 42 squared. And this number is going to be equal to 14 divided by the square root of 43. Excellent. So we now have an answer. What is the distance between the point P and the plane W? So let's draw a picture of what's happening here. This is my set W. These are my two vectors now, u1 and u2, that are perpendicular to each other. Then I have a point P, and I'm projecting P onto W. So I have a 90-degree angle here, and this projection would be the projection on P onto W. And what I'm seeking for is the distance between P and W here, and I'm going to emphasize this distance by writing this in red here. It doesn't look great, but it's really hard to write here with this pen, but we are looking for the length of that vector. That's what we did, and we know that such a distance d is going to be equal to 14 over the square root of 43. You can also get the same answer if you approach the problem differently, which is by, for example, instead of considering the projection of P onto the plane, you can now consider, for example, the projection of P onto the normal line to the plane. And again, you will get the same answer. Surely, the alternative way that you would get by taking the normal to the plane would be much faster. But again, this is a technique that you can expand and use in many situations. So that would be the purpose of this technique that we just looked at. Thank you.